So good afternoon to everyone. So I'm really happy to stand in front of you and give this lecture. So as you have heard the last lecture approach was quite different, and then the way I teach. So that is the reason I choose him, because they are taught in such a way that they want to see the chemical spectroscopy through the physics view. So lots of mathematics are there, and he knows all the derivation, I'm sure. He knows all these things. So if anybody is interested in learning that what is the final form of derivation, how it came, he will be able to do it. Because I stayed in that lab 4.5 years, I know that they do those things because their approach is physics oriented. And my approach is mainly to make you understand that how the spectroscopy is used for the chemistry. So overall look that what is Raman spectroscopy, that will be the first one. So in this one, what I decided that before he goes into the Raman tomorrow morning, so let me prepare a baseline. And there will be no derivation in this presentation, all just to have a feelings for the Raman spectroscopy. So that is the main purpose for this lecture. So I thought of giving the first lecture, so some introductory slides are there. This is the electromagnetic radiation. So electromagnetic radiation starts from the lower energy radio waves to the highest energy gamma rays, and you have the cosmic ray, which is usually you don't get in the earth, that's why. And remember that our eyes, which is also a detector, detects only this small part of the whole electromagnetic radiation. And based on the different electromagnetic radiation, or based on their wavelength, we can we can characterize the spectroscopy in different spectroscopies. Like if you use this gamma ray, then the spectroscopy which is known as Mossberg spectroscopy. And then if you use X-ray, then this X-ray spectroscopy. You use UV visible radiation, then that spectroscopy is called UV visible spectroscopy. And the change in the molecule that is happening is the electronic transition. So this same UV visible spectroscopy is also known as electronic spectroscopy. So this is written that change in the electronic distribution for this UV visible. And this is inner electron, this is outer electron. So X-ray is inner electron, this is outer electron. This is a position change in the nuclear position. And then this is the change in the configuration. Configuration means if you have a dielectric molecule, they are change in the configuration. So this comes under the infrared radiation or vibrational spectroscopy. Vibrational spectroscopy actually a bigger aspect consisting of two kinds of spectroscopy. One is that infrared spectroscopy, another one is the Raman spectroscopy. And if you talk about the rotation of the molecule, then that comes under the rotational spectroscopy, and the radiation that is used is a microwave radiation. And similarly, the spin resonance spectroscopy, these two comes under the spin resonance spectroscopy. One is the electron spin, which is known as ESR, another is the nuclear spin, which is known as NMR. So this is the overall spectroscopy. So this is a really big. Nobody does work in all the spectroscopy. Even nobody does work in one spectroscopy consisting of everything. Say like this person, or we work in Raman spectroscopy, and when you talk about Raman spectroscopy, you think like we do everything related to every type of molecules, but it is not true. So we use mainly the condensed phase, means molecule is in solution. There is a different kind of people who are working gas phase spectroscopy. So even in that, there are people who are using Raman for the biological sample. So even in the Raman, there are 3-4 sectors are there. And usually people do not accept, say, superficial way. Otherwise, the hardcore people remain in one particular topic. Like if you do the Raman spectroscopy of condense, usually condense one. But nowadays, people are, like Professor Hamaguchi's group, they are trying to use their fundamental Raman knowledge to complex system. Complex system means biological system. Because biological system is so far not yet touched, not yet understood, because it is complex. Chemical system or the system that you are making in your lab, this is much easy compared to the biological system, because in chemical system you have a solution, you take some 3 ml of say hexane, ethanol, anything, and then you put a molecule in that, and then you study that one. You know that you have one molecule, and whatever spectra, whatever things are coming, that is coming for the molecule. So you can analyze nicely, but there is no unknown factors. But when you are talking about the biological tissue, you have many types of molecules, many types of molecules, and most of the molecules you do not know. So that makes the situation very complex. So these people who are established in that simple system, now they should try to use their knowledge to unearth this kind of complex system. So these people are moving towards the biological system. But nobody can study the biology and be the expert of Raman spectroscopy. If you want to be the expert of the Raman spectroscopy, then you have to do the gas phase or simple solution Raman spectroscopy. And then you use your knowledge for the complex system. So this is already he has discussed, and this one usually I tell the BSc students to understand this. What is this absorption, emission, and how to visualize that spectrum. Spectrum, you see, this is your light source. Always spectroscopy means light matter interaction. As he has said, nicely he has said the light matter interaction. When that light and matter interacts means when that will be absorbed or scattered, then what happens? Then there is a transition from one energy level to the another energy level. Which energy level is associated? That depends on what kind of spectroscopy you are studying. If you are studying microspectroscopy, then rotational energy level is associated. If you are studying vibrational spectroscopy, then vibrational energy level is associated. If you are doing, say, UV visible spectroscopy, then electronic energy level is associated. Ultimately, it is from transition from one energy level to the another energy level. And how it appears in the spectrum? So I do not have any molecules, say here. So light and then prism to separate. Spectrum is separation of light. So traditionally, nowadays we don't need to use the prism. That grating works for the prism. So now you do not have any molecule here. So what you see that this all the lights emitted by this bulb. So all the lights are there. This continuous. So all the lights are there. Now, and if you have, now go for this one. Now, you have this light source, you have the prism to separate. In between, you have a cold gas. Cold gas means gas molecule which is not excited, which is in ground state, which can absorb some light. So the gas molecule you put in between light source, in between light and the detector. Detector is there. So what happens? This gas, if it interacts with the light, then it absorbs some, because it's a cold one, absorbs and go to the excited state. So it absorbs some of the radiation, some frequencies of the radiation, some wave number of the radiation. So if it absorbs, what will happen to this one? Some frequencies will be missing. That black line is the missing of the frequency. And this is the spectrum. Okay. Now, what happens if you have hot gas? Hot gas means excited gas. So whenever something in the excited state, it doesn't remain in excited state forever. It has to come down. So come back. So comes back means it will give some radiation, and that is what it is giving. So in black screen, you get some lines, and this line is that these are the wavelengths. This has emitted. So this is called emission spectra. This is called absorption spectra. So this is another good image I have taken from internet. You see, this is the, say you have all the radiation in the beam, in the light source, and so this is the light source, and you are putting this light source on the a beaker or a conical having the solution. So if it absorbs, then something will happen in the molecule. So something is happening, molecule in the ground state going to the excited state. And what it absorbing? It absorbing the green wavelength. So you have all the wavelengths, red, green, purple, and all these things. So molecule is absorbing the green wavelength. Why it should absorb? There are certain conditions. The simple condition we can tell that energy level matches it well. So it absorbing the green light and going to the excited state, and is going to the excited state. So if it absorbs the green light, what will happen? You have everything except the green radiation. So now if you plot in terms of the spectrum, now you plot, spectrum can be plotted in two ways, many ways. So here you have to always see what is in the y-axis caption, what is the x-axis caption. Here it is the wavelength with respect to wavelength, and here two ways it is plotted. This is a photon intensity. So this black line, what this black line says, the black line is saying that it is transmission spectrum, 100% transmission, because it is there 100%, it is there 100%, so it is 100%. And in case of green, you see it is 0%. Green is not being transmitted because green is absorbed. And again, you have all these things transmitted 100%. So you see a spot for the green light, absence of the green light. This is if you plot transmittance. Now if you plot absorption in this axis, then you see this is the peak, this dotted line. Okay, so this is how this spectrum comes. When you are talking about spectrum, few things you should learn, because my purpose is to make a foundation. See, it's whenever you put, if there is a interaction and you get a signal, but often you see those who does the experiment, they often see that sometimes signal doesn't come properly. So whether the signal is proper or not, that is given by a quantity which is called SN ratio. SN ratio. SN ratio will say whether the signal to noise ratio is good to present. There are many ways which can be used to improve the signal to noise ratio. So this is say you have used 20 millisecond exposure time for the experiment, and you get this dots are your data. And the spectrum comes out of the fitting. So you fit it, and this says that signal is poor, and you have fitted it to it. So this is the fitting parameter, and this is the dots of the signal. So you record, instead of 20, you make it 10 times more, give 10 times more, so the more photon comes in, and then 200 millisecond, and you see the signal is more consistent and the fitting is better. You give more, then it is more. So usually, if you increase the number of recording, then the signal increases by that many times. Like if you do, instead of one time recording, if you do 10 times recording, your signal get enhanced 10 times. But the noise doesn't get enhanced by 10 times, it gets enhanced by √10 times. So signal to noise, you have a gain of √10. So this is how this works. You have another issue of resolving. Resolving means, say you have two dots, you want to see these two dots, and you have a microscope. Not all the microscope allow you to see the two dots. If you have an expensive one, then you see the two dots clearly. If you have a cheap, then you don't see the two dots clearly. You see the only one dots. So resolving the two different spots comes under the resolving power. Now, problem is that in one hand, you want to increase the SN ratio, so you have to put more light. On the other hand, the moment you put more light, then there is a possibility that this kind of two dots will be mixing to one. Because the more light means this exit slit. Exit slit, you have to widen it to get the more intensity, but the moment you widen the exit slit, you lose the resolution. So that's why it is written that spectroscopy is a continual battle to find a minimum slit. Minimum slit you are giving means minimum light you are giving. So you are compromising with the signal to noise ratio. Continual battle to find a minimum slit width consistent with acceptable SN ratio. So this is, say, a spectrum. This is a spectrum. This is a band. This is a line, depending on the type of the where you are using it. And there are usually two. There are three also possible, usually Gaussian and Lorentzian. This red one is Gaussian, and green one is the Lorentzian. So we get we are expecting this kind of spectrum or band. So the spectrum or band, sometime it comes very weak, sometime it comes strong, sometime it comes width. Width is quite big, sometime it's narrow. So what are the factors which contributes in the intensity? Means whether you will see a weak or a strong, whether you will see a narrow or. So this is there are two things. One is the intensity and two is the width. Width means this is the width. How to define it? F, W, H, M. F is full width. Full width. Full width where? Full width. So if it is your spectrum, then full width, this is also full width, this is also full width. So where is the full width we are talking about? Full width at half maxima. This is a maxima, half is here. So full width at half maxima. So this is called FWHM. So FWHM is narrow or wide, intensity is small or big. That what are the factors that contributes? That is, we will quickly go through. Okay, first now we are discussing about width. First factor is the natural line width that is given by the Heisenberg uncertainty principle. Why this naturally, why it says natural? Because ideally, as I said, if it is the energy level 0 and if it is the energy level E1, then you excite, goes like that, and that's where the spectrum appears at the wave number or energy between the difference of E1 minus E0. So E1 is a number, E0 is a number, so you should get a line having no width, but that is not possible because there is the Heisenberg uncertainty principle says that this transition has inherently some line width. That is because of the fuzziness of the excited state. Excited state is not precise, so there is a fuzziness. So this fuzziness creates the minimum line width. So that is given by Heisenberg principle. This Heisenberg is a German scientist. What it says that you know these things, delta x, moment, this position and momentum, this minimum you should expect h cross h by 2 pi. This is the minimum. So if you do this one, delta E into T, so the delta nu is the line width. Delta nu. So what is the delta nu? Delta nu is proportional to minimum is 1 by delta T. What is delta T? Delta T is the lifetime at the excited state. How much time it is staying in the excited state. So if you think that we are considering the electronic spectroscopy, so what is the delta T value? Usually, delta T value is usually in nanosecond. Means how much time a molecule resides in the first electronic state, S1, usually in nanosecond. Okay, 1 nanosecond, 0.5 nanosecond, means we are talking about the order, in the order of nanosecond. So if you think, then it is the 10 to the power 9. So 10 to the power 9, if you go to the higher one, so or maybe 10 to the power 8, they are considering, then you get the delta nu, means bandwidth, is 10 to the power 6 Hz. So instead of expecting a line, Heisenberg's uncertainty principle says that you can no way get a spectrum or band which has less than, for electronic spectroscopy, considering delta T is 10 to the power minus 8, the line would become 15 into 10 to the power 6. So you have at least this big 10 to the power 6 Hz width should be there. So this is one, but this is more important is other things, other effects. Other effect is Doppler broadening. Doppler broadening is like if a train is moving and it is giving a whistle and your ear is the detector, then if the train is moving away from you, you will listen a frequency which is not the frequency that the train is emitting. And if the train is coming towards you, you will listen a frequency which is again not the frequency the train is emitting. You will listen in this case more than what is actually emitting. And this detector is the detector which gives you the information. So in spectroscopy also, you will have a detector. So the detector, what it detects? It actually detects the different one. So what is the change in the detection? So you can use this formula. This V is the velocity, a frequency that it is recorded, and it is the original frequency that is emitted plus minus 1 velocity by C. And it is seen that for this nitrogen at 300 Kelvin, and if you talk about the velocity is 517 meter per second, velocity of nitrogen at 300 Kelvin, 517 meter per second, then and the nu zero value is 10 to the power 15 hertz. Because of the Doppler effect, you will get a broadening, and that broadening is even 400 times more than the Heisenberg uncertainty people, whatever it gives. You see, it is 10 to the power 9. So there it was giving 10 to the power 6, now it is giving 10 to the power 9. So this also this affects more than the Heisenberg uncertainty principle. And this one is the collision broadening. Collision broadening means, as I said, that there are different spectroscopists, like some spectroscopists work in the gas phase, some spectroscopists work in the solution, some works in the solid. So gas phase spectroscopists, they say that the solution spectroscopy is not the real spectroscopy because you have the effect of the solvent molecule. So here you can see, because if you use a molecule in the solvent, then this excited state of the solvent quickly, this excited molecule collide with the solvent molecule and it comes back to the ground state. So its lifetime is less. So in solution, the lifetime is less. And now if the lifetime is less, then this goes up. So in solution, you see a broader band than the gas phase. So gas phase spectroscopy, anything you record in gas phase, you get a sharper band than the corresponding solution state. So these are the three for the effect for the width. And now the intensity. Intensity has three parameter which decides the intensity. One is the transition probability. Transition probability is like you have a class of MSc first year, 100 students, and then we are thinking, or BSc first year, 100 students, and then we are thinking that how many students, or what is the probability of a student going to the BSc third year, from first year to the BSc third year. What is the probability? This nil, because it is forbidden. So if it is forbidden, that means you will not have any intensity. Means 100 students in BSc first year, you will have 0 in BSc third year, because the system does not allow any student to promote from BSc first year to third year. So it is the probability is 0. Similarly, this transition probability says whether it is allowed or not. Two factors are there, two forbiddenness is there, and we discuss the forbiddenness and rest of this allowed. What is the forbiddenness? One is the spin forbidden. Spin forbidden says that one can think of a transition from one spin state to another spin state where the spin multiplicity do not change. So if it is a singlet, from singlet to singlet. If it is triplet, triplet to triplet. Spin multiplicity should not change. So if there is a change in the spin multiplicity, no intensity, because transition is forbidden. But it is not strict, it is a guidelines. Another is the symmetry forbidden transition. Symmetry forbidden transition says that if there is no change in the symmetry, then there is no change in the dipole moment and the molecule do not interact with the electromagnetic radiation. For example, if you have 1s and 2s where symmetry is same, then there will be no transition. On the other hand, from 1s to 2p, there will be transition. Simple logic is that there should be change in the dipole moment, redistribution of the electron density. So that is not happening there, it is happening there. So two factors which contributes, which guides you for the symmetry one and the spin. And the population is that population, not the population of the overall, that is the different one. This population says that when you are talking about transition from one to another, so how many molecules are there in this state? It is like you have a class of 100 students, and usually in BHU 90% students gets promoted, or maybe 95, so 90 students. So how many students qualified in last year? I can say 90 students. So it's a huge number. But if you go to some other university or institute where number of students is 20, so how many students, even if it is 90%, even if it is 100%, it's just 20. So population matters. So here also, if your population in that originating state is more, so you will see more intensity, obviously. Another one is the concentration or path length. This one you have studied in your BSc and MSc. So if you have a solution in a cuvette, and the cuvette path length is usually 1 centimeter. So if it is 1 centimeter, then the light is passing through the solution of 1 centimeter. So it is getting a 1 centimeter path length number of molecules through the 1 centimeter. Now imagine if this solution, instead of 1 centimeter, if we take a 1 millimeter cuvette, so light will pass through only 1 millimeter. So the intensity will reduce to 10 times. Similarly, if you increase the concentration in this molecule, this concentration population is different than this one. This is the concentration of the solution. If you increase the concentration of the solution, intensity increases. And this path length and concentration, these two are together, is known as Lambert-Beer's law. This Lambert-Beer's law is a very simple law and developed 200 years before, but still we are using it. What it says that log I0 by I0 is the incident light, I is the transmitted light. So I0 and I will be different if your solution has absorbed some light. So log I0 by I, this is called absorbance or simply OD, optical density. This is equal to epsilon, this is epsilon, C and L. C for the concentration, C is the concentration, and L is the path length. L is the path length. Usually we take 1 centimeter, so L is the 1. Now, what is the importance of this epsilon? Epsilon is called molar absorptivity. Epsilon, if you have a molecule A and whose epsilon is say 1000, and unit is very easy to determine, this unit, because this is unitless. So epsilon unit will be 1 by Cl. Concentration, you know that mole per liter, and this is centimeter, so inverse of that, this unit. Whatever this unit I am talking about this one. So A, say you have two molecules, A molecule and B molecule, and one is this one, another is say 10 to the power 5. What is the difference between A and B? By seeing this number, you can tell that B molecule have a light absorbing power almost 1000 times of A molecule. Okay, so this epsilon is a very important parameter. Often you will see, we always plot UV visible spectrum wavelength versus OD or absorbance. But in true sense, if you want to make it more informative, then instead of OD, you should plot it epsilon. So since time is not enough, so let us go to this Raman spectroscopy. So as you know, the Raman is an Indian scientist who got Nobel Prize out of doing work in India. And in fact, he has done all this Nobel Prize winning work in cultivation of sign in Jadavpur. So a few pictures that I have taken from this internet, I think Nobel Prize website. So here Raman is teaching, and he is a good teacher. He was a good teacher, and he was very confident teacher, and he was, as a person, he was also very confident. He is confident unlike many Indians. Okay, so this picture, he is along with the other Nobel laureates, and this is a picture where he is talking about his instrument to the foreigners. So imagine this is happening in the year when we were not independent. Okay, when British was ruling. So ruler, he is explaining his instrument with full confidence to the ruler. So in many aspects, we have seen that Raman was very confident in whatever he has achieved. That is a very good thing. Now, introduction of Raman. Raman spectroscopy is not like a IR spectroscopy or micro spectroscopy. Raman spectroscopy in that sense is quite different. It is a light scattering spectroscopy. Light scattered, not that light absorbed by the molecule. It's scattered by the molecule. And he first reported this spectroscopy, this result in 1928, almost 100 years, no? And he got, it is said means that must be true, because that time that there is no instrumentation, and it was just like a normal building was there in cultivation of science, and he was a foreign, some government service under the British rule, and he used to see the building is there, and after the work he used to come to the building and he used to work. He was not a regular scientist in that sense. And when he got good results, then he left that job, well-paid job, to take this scientist job in cultivation of science. So there is no instrumentation, nothing. So what he did is that he used sunlight as the source of excitation and his own eye to detect the change in the frequency. And that is not that difficult if your system helps you. So like if I switch on this red light and then red light is becoming green light, your detector can signal it. So he used sunlight and as a source, and his eye as a detector. Now it is 1928, the world knows that there is a new spectroscopy. But this spectroscopy was not that much popular. Nobody was carrying Raman spectroscopy till 1960s. It's a big time. It's a 1930s to 1960s. 30 years is not a joke, no? Because nowadays you see super result spectroscope within 10 years it come into the market. Whatever happens in the lab, and then if that work is recognized by somebody like Nobel Prize Committee, then immediately it come to the market, almost immediately, within 5 years or so. But that time, imagine that 35, 30, 40 years nobody was using, because Raman spectroscopy has some inherent problem. Why? Because this signal that you get is very weak. And you need to have a strong excitation source. So you need to have a good detector, you need to have a strong excitation source. So that time they were using sunlight or mercury light, which was not good enough to study many molecules. So after the invention of laser, when laser came into the market, when good optics came into the market, when good detectors are developed in the market, then Raman suddenly saw this flourishing. So now it is, people say, or the scientists feel, that Raman spectroscopy is one of the most promising spectroscopy as of now, which can really find or unearth very unique information of biological system. So what is Raman spectroscopy? Now you think that you are giving a green light on a molecule. Now it is a scattering spectroscopy. Now what can happen? That just this can scatter the same light back. So that is the green light. You are getting back the green light. There is no change in the frequency. So this is called Rayleigh scattering. Rayleigh is also another Sir Rayleigh is a very, that time, I will show the next slide. That time he said all these things, that there will be no change in the wavelength of light or frequency of light. Other two things that also another person said, that you may have a loss of energy. If you have loss of energy, green, loss of energy, you have a red one, red frequency back. So that is known as Stokes-Raman scattering. And you may have a gain in the energy. So green become blue, so that is called anti-Stokes. So if it gives you back the original frequency, then it is Rayleigh scattering. If there is a change in the energy, that becomes the Raman scattering. This is the slide. This is a kind of homage to my PhD postdoc supervisor. I didn't do any Raman work during my PhD. I did all my Raman work during my postdoc. So he was my postdoctoral supervisor, Professor Hiro Hamaguchi. He's a very big shot. He's one of the most prominent Raman spectroscopists in the world. He has got 2 times Purple Ribbon Award of the Emperor. He's a very fantastic person. He's a very excellent, excellent teacher. I hope that someday I will bring him here for the. His supervisor is this one, and he used to say spectra are letters from the molecule. Okay, what does it mean? It means that when you get a spectrum, like last one, you get a spectrum, and this spectrum, if you can read, you will be knowing from the, you will be knowing something about the molecule. So that is a very big thing. So he said the spectra are molecule, he says, his professor, and what he says is that this Raman spectroscopy is a third eye for him. Third eye. So this is the third eye. So if you can analyze the Raman spectrum, then you really have a third eye, because you know more than what other people know. So you see the Rayleigh discovered 1871, and then Adolf Schmickel, one Austrian scientist, in 1923, almost simultaneously or 5 years before of Raman's discovery or Raman's reporting, he said that inelastic light scattering. This is elastic light scattering, and the Raman is inelastic light scattering. He has already said that there will be inelastic light scattering, and that means loss of energy. But only difference with the, he did not get Nobel Prize. He did not get Nobel Prize, but after 5 years, Raman said the same thing and he got the Nobel Prize. What is the difference? Difference is that he has said theoretically. He has said theoretically, this is the paper. And Raman has done it. So just by telling in theory is not enough. World doesn't accept that one, because in theory you can tell many things. You have to do it. You have to show it. Raman, as an experimentalist, he has shown it. That's why he has got the Nobel Prize. And who is this person? Anybody know? So he is the second author in the Nature paper where Raman has given his theory, which actually fetched him the Nobel Prize. He is another author of that Nature paper, along with the C.V. Raman. But you see, nobody knows him. So in research it happens. It is not that every time you work and you are getting recognized. Sometime you are recognized, sometime not. It depends on who is your opponent. If your opponent is very powerful, then you are small. Okay. And this one, this used to be one slide of Professor Hamaguchi. He has recorded this one. This is a Raman spectrum of carbon tetrachloride, CCl4. See, this is how it looks like if you have a photographic plate and the photographic plate is detecting the light. Then it looks like this one. So this is a real image. That's why I have showing you. This is the strongest one, and this is the known as Rayleigh scattering. This is in the lower wavelength range. So this is Stokes shift. This intensity is less than this one, but much less than this one. This will be very strong because it's a Rayleigh scattering, and this one will be much less than this one, but this will be much more than the corresponding anti-Stokes. So this is Rayleigh scattering, and this one is called Raman scattering. Raman scattering for the lower range wavelength is known as Stokes-Raman shift, and the higher one is known as anti-Stokes. So through energy level diagram, we can understand this one soon. So infrared spectroscopy is the this also vibrational spectroscopy that depends on the absorption of the light, and Raman spectroscopy depends on the scattering. Their selection tools are different, and Raman spectroscopy, since it is a scattering and it's the change in dipole moment is not the criteria for molecule to have a Raman spectroscopy. The change in the polarizability is the item that you have to monitor, change in the polarizability. So if there is a change in the polarizability of the molecule, then it gives you the Raman spectrum. And most of the molecule, there is change in the polarizability. Even in case of the diatomic molecule, homonuclear diatomic molecule like H2, N2O2, which doesn't give you the IR spectrum, but they will give you the Raman spectrum. What happens? These are simple things that if you have a molecule and then an electric field is applied on the molecule, then there will be a redistribution of charge. And redistribution of charge will create a induced dipole. And the induced dipole, which is mu induced, dipole induced. So this induced dipole is proportional to the electric field that you are applying. The more strong light you are giving, more stronger induced field is generated. And the proportionality constant is alpha, which is the polarizability. So your starting is that mu induced because of the incident light, and that became alpha E. This one maybe he will, this is just to tell that whether a molecule will have a Raman active vibrations or IR active vibration, that can be found from the character table. So this is a character table of C2V molecule, C2V type. So water is the example. Here four normal modes are there, and in that one normal mode cannot be detected by the IR because it is absent, but all the modes can be detected by the Raman. So in this particular case, all the modes will be detected by the Raman, but one mode cannot be detected, A2 mode cannot be detected by IR. So if you use only IR, so one mode will be missing in your experiment, but if you use Raman, you get that mode recorded. So this one, leave it. Instrumentation, I think he will be using it, but overall instrumentation is you should have a laser because you need to have a strong excitation source. And then usually you have a beam splitter. That beam splitter, this laser light comes and it falls on the sample. This is in backscattering, it is recorded on the sample, and from the sample, whatever the Raman signal is coming, that this mirror allows, and this will go to the spectrometer. So what is necessary is that you need to have a laser excitation source, you need to have a beam splitter, you need to have a spectrometer, you need to have a detector, and of course the sample. This instrumentation I am sure he will be describing. Or you can have this one, that is the one I used to use. So here you have a laser excitation source. ND filter means neutral density filter to reduce the intensity of the laser, because laser can be very powerful and you need a very small amount of laser to the sample, because maybe sample is the organic sample, a sample may be the biological sample, then you need very small amount. So now you reduce the energy, and then this beam splitter, so this goes like that. Objective mirror, that is like your microscope, it allows you to excite, and the same microscope will allow you to take the Raman scattered signal, and that signal will be different than the excitation wavelength. This color is not the correct one. This color will be different, because you have seen rarely will have the same color. Other things will be different color. So this will go. This is dichroic mirror. Dichroic mirror means it allows the other frequency to go. Okay. So it will go, then mirror, notch filter, and then pinhole. This nowadays pinhole technique is very popular. So that is called confocal. So it is a confocal Raman microscope. Confocal Raman microscope, pinhole is necessary. So and then you take it to the grating to spectrum. Okay, CCD, this is a detector, grating, this is spectrometer, this is detector, and then get the spectrum in the this one. This is very complex. If you have a very expensive instrument like this one that we have in our department, it's almost like 1.1 crore. This is this model is LabRAM, high resolution HR. This made by Horiba. You can have various other models also, like this is a Renisha. So this is another company. You can have such kind of small instrument also. These are all Raman. This is also Raman. This is also Raman. Different companies. You can have handheld, like this kind of portable things, and you see it is detecting some forensic or medicine something. So this kind of is a handheld one. Or you can have a complex like this. So why it is complex? You see what are the laser excitation source are given: 229, 244, 264, 325. Hardly this kind of laser will be there with the Raman machine in common field. Maybe 1% or 2%, because they all belong to the UV radiation. So in UV length. This is visible, 442, 488, 532. We have 532, we have 633, and we have 785. So these are normal, these are common. So you see so many excitation wavelength consisting multi-wavelength Raman system. So last one is very cheap. This is extremely expensive, extremely expensive. On the other hand, this is what Sir C.V. Raman made it. It is still there in Cultivation of Science. You see, it's just what is there. It's just for the light, sunlight to come in, and maybe some camera lens is there, and maybe he used to see from there. So this simple machine, now you have a multi-crore machine. Where is the difference? This is Raman with his instrument. The difference is that we want to see more. Always we want to see more. It's like you have a 10,000 rupees mobile and somebody has 1,20,000 rupees mobile. What is the difference in camera? Camera is that if you use 1,20,000, your resolution is much more. You will be seeing much brighter image, much prominent image than the 10,000. So in spectroscopy, it is the resolution. Resolution means whether you are able to see the band separately. So the more band you see, more information, if you can analyze, more information you know about the molecule or the system. So here is the high resolution, it's a low resolution, not that much difference here. So for say this band. This band is just splitted here, but here it appears very nicely cleanly. Here. Here you see this band is absent here. So here every band is very clearly seen. The more you see, the more you know about the molecule. If you know more about the molecule, that means you are ahead of others. So you pay more money to see more things. Okay, so that is the simple equation. You have a Raman spectrometer of maybe 20 lakhs, and you have maybe some 4 crore or 5 crores, depending on what are the excitation source you are using. So if you have a band, these are the things you can find out analyzing the band. So you can find from the band density, you can find the polarizability of the chemical bond, band intensity, how intense. From the band position, you can understand about the chemical structure. From band shift, say you have original band here and then it shifted here, then you can find out the stress strain profile also. Band width will talk about the crystallinity and defects. You can talk about the polarization, orientation, and the band ratio. If you have 2 bands, their ratio also will give you the relative concentration. So Raman spectroscopy in general of 2 types. One is that vibrational and another is rotational. So we start with the rotational Raman spectroscopy, and the theory is same for the vibrational except a few difference. So if we, so did we take 1 hour? Okay, please. Yeah, come in. So let us go to this one. So we have studied this mu. Mu is alpha E. And then what is the mu? Mu is the induced dipole moment. Now the magnitude of polarizability varies during the rotation. Now the rotational Raman spectrum, it is varying during the rotation. And what is the variation? Variation is given by this one. Alpha is alpha 0, R stands for the rotational one. And for vibrational one, we will write the V. So alpha 0 R plus alpha 1 R sine 2 pi C, these are all known. And the 2 times of the rotational frequency of the molecule. Why 2 times? It is like this one. If you have a diatic molecule like this and this, 2 atoms are attached, and now this radiation is coming from this side. So radiation, classical approach, radiation is seeing this molecule once now, and since it is rotating, and when it is rotated 180, then it is seeing the same thing again. So in a complete rotation, it's seeing twice of the same spot. So that's why 2 into new frequency. So that is why you will have 2. Now, if you put this E and this alpha, these 2 expression, and then simple, just elaborate. 2 signs term can be elaborated in terms of cos A plus B, cos A minus B. Then you have 3 terms. Because this one, first one with this one will be this one. This term, because you are multiplying alpha E, so this multiplied by this, so this is this term. Then this multiplied by this sine term, this sine A sine B can be expressed in terms of 1 by 2 cos A minus B, B minus A plus B. So A plus B term, A minus B term. So you have 2 terms, this is sine, is changing to cos. Now what happens, now we are interested to see what happens in the frequency. How many scattered radiation we will see. So this frequency is here, this one, and this one. So this is nu T. What is the nu? Nu is the frequency of the light. So one radiation you will see where is no change in the frequency of light, and that is known as Rayleigh scattering. And another one is that frequency of light plus the molecular frequency property, rotational frequency, plus 2 nu. 2 term you know, 2 nu. So whatever your energy you are giving, you are getting more. So nu plus 2 nu rotation. So this is known as anti-Stoke. Whatever energy you are giving nu, you are getting back more. And this one is, this you are giving minus this molecule. So this one can be understood better if you see the diagram. So we have now 3. One is the Rayleigh scattering, anti-Stoke, Stokes-Raman. Intensity of Rayleigh scattering is the highest one, then Stokes, then anti-Stoke. Now what happened in terms of molecular energy levels? Say, this is put in terms of vibrational Raman spectroscopy. Say your molecule is here, and then it goes to virtual state, and it comes back directly from there to the originating state. So there is no loss of energy. So this is known as Rayleigh scattering. Now your molecule is again there, the ground state, and it goes to the same virtual state and comes back to a state, vibrational state, which is V is equal to 1. Where it will come back, that depends on the selection rule. Okay. For in case of rotational one, this change will be delta J plus minus 2. In this case, it is plus minus 1. So it comes back here. Now, important thing is to understand is that the band you get, it is not this difference. In IR case, it is the difference. But in this case, it is that. The difference of this minus this. So the band will be this one. That is why in the Raman spectrum, this axis is known as Raman shift. Shift from whatever energy you have given and how much shift. The shift is this one. This is the shift. So this is known as Raman shift. So this is the Stokes scattering. Now anti-Stoke, that often student ask that how you get more energy. You are giving certain energy, how you get more energy. You see, because of thermal population, the higher energy levels are also will be occupied according to the Boltzmann distribution. If transition happen from the higher energy level and it goes to the virtual state, I think virtual state he will be talking about tomorrow. It goes to the virtual state and then it comes back following the selection rule that delta V is 1, then the difference is this one. This difference and this difference is exactly the same. That is why this in Raman spectrum, you see at the center position is the strong Rayleigh band, that is this one, and from the center, wherever the Stokes shift comes, if it is a 400, then in that direction it is 0. In that direction, exactly at 400, your anti-Stoke bands will come, because both indicates the same difference of the energy level. And these bands are coming because of the difference of energies. It is not directly absorption. So that means in Raman spectrum, you will have a Rayleigh scattering, which is not necessary for us, which has to be eliminated by some filter or somewhere. And then you get a strong band because of the stroke transition, because of the stroke. And then in the negative side, you get the anti-stroke band. The intensity of the anti-stroke band will be much less than the Stokes one, because the population of this energy level will be much less than this energy level. Okay, so in books you will be seeing this kind of, this is already I have told you, this is the difference, this one is the difference, and that difference is plotted here. Often students confuse that this is showing the transition. Actually, this is the difference, it is plotted here. So this difference comes, this is the energy level diagram, and this is how the spectrum will appear. The Rayleigh will be much more stronger than the Stokes and the anti-Stokes. Okay, we have to stop it. Maybe next class we'll start, because